Okay. Thank you very much for coming. This is the last talk of a long day, so also thank you very much for staying. And the talk is about artificial black holes. So how do you make your own black hole in the laboratory, in the basement, or in the kitchen sink, depending on what you like. And let me start this with a very big picture and a big question. The question is, are there quantum effects in astrophysics? So are there some scenarios where quantum physics is relevant on an astronomical scale? And you may say, yes, we know already about one, and that is caused by cosmic inflation. So not to be confused with financial inflation, although financial inflation may also reach cosmic scales. I hope the inflation you are experiencing doesn't. And cosmic inflation is caused by the rapid expansion of the early universe, and in the first instance of its existence, the universe expanded exponentially. And while doing so, it amplified waves. So it acted as a broadband parametric amplifier. All sorts of waves were amplified in it. And then at some stage, the universe, the inflation stopped, and then later the universe cooled down, and it was possible that plasma formed. But these fluctuations that were amplified during the early stages, these were quantum fluctuations that were amplified, they then made an imprint on the early plasma of the universe, and that resulted in fluctuations of the microwave background. So these fluctuations, they have been measured to a high degree of precision in experimental cosmology, and they confirm that this process has taken place. So there are very good indication for inflation and for the parametric amplification of quantum fluctuations in inflation. Those quantum fluctuations have then created the seeds of large-scale structures in the universe, and that is, on one hand, it's amazing that quantum fluctuations can have played a role in creating very large structures. On the other hand, they also show that, in fact, there is already some evidence that quantum fluctuations do appear in cosmology. But this is not what I want to talk about. So I want to talk about something else, and another very well-known effect in astrophysics that was predicted by this gentleman here, not when he was in The Simpsons, but before, and published in this two-page paper in Nature, and then in a subsequent publication in Communications and Mathematical Physics. What he predicted was that if you take a black hole, then a black hole is not something that is black, but it is radiating. And in fact, this paper is called black hole explosion. So what it will do is it's radiating, it's sending out its energy, and therefore it's shrinking. And in its final stages of shrinkage, it radiates even more and more and more, such that in the end of its life, the black hole is going to explode. So that makes the title of this paper. So black holes are not black, they're radiating. They're radiating because of quantum physics. So they are able to create pairs of particles and antiparticles from the quantum vacuum. And the vast majority of those pairs will actually be massless particles, like photons. So photon is its own antiparticle, so photon pairs are produced, one at one side of the horizon, the other one at the other side of the horizon of the black hole. And that's an interesting phenomenon. It's an interesting phenomenon because it unites three different areas of physics. So and you see this from Stephen Hawking's formula for the radiation temperature. So and you see it already from the constants of nature that enter this formula. So what you see is there's a C there and big G, so it belongs to the research areas of relativity and gravity. There's an H bar in front, and you know it's a quantum process, so it belongs to quantum mechanics, but it is also thermodynamic. So there's Boltzmann constant involved here, that belongs to thermodynamics. In fact, the first person who has predicted that black holes have to do with thermodynamics was Jakob Bekenstein, who sadly died this year. And so he was the one who laid the ground for Stephen Hawking's work, who then find that not only Bekenstein's prediction is true, that there is some thermodynamic associated with black holes, but he found the prefactor. So he found how much of that thermodynamics then turns into heat. So how much of that is really related to a temperature of the black hole. So there are three different areas of physics that are not normally connected with each other. In particular, we have little idea what quantum mechanics and gravity really have in common. Here is an effect of physics where they come together, so by studying them, we can perhaps understand better what those connections are. Now, this is the plus side. The minus side appears when you set numbers into this formula. So you can rearrange things a little bit and you can work out what is the characteristic wavelength of the radiation emitted by a black hole. And it is something like 2 orders of magnitude larger than the Schwarzschild radius of a black hole. Now, the Schwarzschild radius of a black hole that is made by the collapse of a star cannot be arbitrarily small. There is a minimal mass required for that. And the order of magnitude is a few kilometers for this. So the average wavelength of the radiation emitted from a black hole made as a consequence of the collapse is in the order of 100 kilometers or more. So a few hundred kilometers. This is radio waves. So we're talking about radiation of very long wavelength or of very low temperature. Now, this radiation has to compete with the cosmic microwave background that is in the order of, because it's microwave, it's centimeters. So it's a radiator in a much, by 8 orders of magnitude hotter bath of radiation, so it would be, even if you would have a completely quiet black hole, it would be very difficult to observe this kind of process from the black hole itself. So it's very hard to get experimental evidence into it. Then there's a fundamental problem. So if you ask the question, okay, let's accept that there's radiation coming out of the black hole, and then where does it really come from? Let's trace it back in its history. So there's radiation that you have observed, supposedly, and then you trace it back into history, and then back to its origin at the horizon. Now, the horizon of a black hole causes an enormous redshift. That means if you go back, then you have to compensate for that redshift, so you have to blue shift the radiation, and you have to blue shift it beyond all scales. At the horizon of the black hole, there's an infinite amount of frequency shifting. And that means that this radiation really comes from very, very short wavelengths beyond any scales we can imagine, and it could be certainly beyond the Planck scale. Then you can ask the question, well, can we trust these calculations at all? So are they not affected by the physics of very small scales where we have no idea about this, and what can we really learn about these things? So this is the fundamental question, so it's the influence of small scales on the radiation of black holes. The practical question is that it's very hard to give some evidence for or against it. Now, that sets the case for artificial black holes. So these are the rubber duck black holes that we want to make. And this field really was pioneered by Richard Wolowik from the Landau Institute, who worked mainly with helium. So he wrote a book called The Universe in a Helium Droplet, and where he meant that helium is helium-free, and where he showed that essentially you can find the entire physics of the standard model in helium. He calls it the helium-centric worldview. So if there isn't anything in helium, if there's some phenomenon not to be found in helium, it probably doesn't exist in nature either. And so that's the helium-centric perspective. So he has, among others, of course, inspired this field. And he was also one of the people who came up with a way of how to make analogs of the event horizons in the laboratory. And it's based on a very simple and intuitive idea. So this is a black hole. A black hole is similar to a river. So imagine we are talking about a river that is flowing towards a waterfall. And this river is getting faster and faster and faster and faster until it reaches singularity faults. Now, this river is populated by fish. These fish, they can swim upstream, they can swim downstream, but they have a finite velocity. Let's call that c. Now, at some stage, the river reaches the velocity of the fish. Then, for the fish fortunate on this side of the river, they can escape, so they can swim upstream. And however, fish on the other side of the horizon, they cannot swim upstream anymore because simply they're slower than their environment. So they will drift backwards until they get crashed at singularity faults. This is a picture, it's an intuitive picture of what a black hole does. So a black hole in space you can picture as some flow moving towards the singularity of the black hole, and the waves, the light waves, for example, they are playing the same role as the fish here. So they have a finite velocity c, and when space rushes towards the singularity at a velocity faster than the speed of light, you have a horizon. So this defines the horizon of the black hole. This is not only a picture, it is also an exact correspondence. So you can show that the equation of waves in moving fluid is of exactly the same form as the equation of scalar waves in general relativity. So you can identify the wave equation with a metric, and this metric depends then on the velocity of the fluid, depends on the speed of the waves. I should have said, so this is of course true for waves, not for fish. So in order to translate this picture into physics, what you do is you place these fish by waves. These could be waves on the surface of the water, these could be sound waves in the water, and it could even be light. So waves in moving fluids behave like waves in a space-time geometry given by general relativity, and these space-time geometries, they are sufficiently large such that the black holes, like the Schwarzschild black hole and Kerr black holes, they can be included in these geometries. So that's one of the advantages. Another advantage is that there is a simple connection between hypothetical physics beyond the Planck scale and the normal behavior of waves and fluids. And this comes from dispersion. So this is a simple discussion of how you see this. So imagine for a second, we're now talking about wave propagation in space, that there is some finite scale. So there is a scale at which space would be discrete. This is like wave propagation in a crystal. So you have now, instead of a wave, you have a set of coupled harmonic oscillators with some characteristic distance and coupling strength. And then you can, what you do is you can, by Taylor expansion, you can turn this into a wave equation. And the leading order where the discreteness of space appears is this term here. It's a higher order dispersion term. And so it says that if you have a discrete underlying structure of space, then the first indication of that structure is dispersion. Now, in reality, so if you work with a realistic fluid, if you study the propagation of waves in fluids, or the propagation of light in optical materials, then this is a natural component. You always have dispersion. So therefore, in these analogs of black holes, that give you a natural way of studying something that you would expect, the first things that you would expect from Trans-Planckian physics to show up. The other advantage is you can all do it at home. So you can build your own black hole if you like, and all you have to do is you go to the kitchen and look at water falling down from the tap. So there's tap water, and you probably have noticed, so when the tap water falls on a smooth surface, then you see these rings here. So you see, first of all, you see a very smooth surface in the middle, and then there's a ring structure formed and further rings out there. This, you may argue, is an analog of a black hole. Why? Because the water that is flowing out there, it's faster than the speed of waves, capillary waves. And so therefore, the surface, no waves can be formed, and therefore the surface is very smooth. Then the water expands. While expanding, it's getting slower. and hence it may reach the velocity of the waves, and then waves are formed. And that's a fluid mechanical phenomenon that is to some extent an analog of a horizon. It is not a black hole horizon, it's a white hole horizon. Because for the black hole horizon, your fluid gets faster, and to form the horizon here, the fluid gets from the outside slower. So it is something that waves cannot enter, whereas in the black hole, waves cannot leave. Or you may also say it's like a sink turned upside down. So you could also imagine waves rushing towards a sink, and then that sink would represent, in fact, a black hole and not a white hole. You can all do this at home, but to really see the beauty of these experiments, you have to use some more sophisticated equipment. This is a beautiful photograph from a set of experiments done with these hydraulic jumps. That's the scientific term. And there you see very nicely these Mach cones formed here. So you see simply by, first of all, you see the smooth surface. So this is not water, this is some silicone oil that was used. And then you see very nicely a formation of cones. And by disturbance, if you would move this out, then these cones turn into ellipses. So you see this transition from faster than wave speed propagation inside to slower than wave speed propagation outside of the structure. Now, but this is not what we want to do. So we want to do experiments in optics. So we want to build an analog, an optical analog of a black hole. Why do we want to do this? Because we are interested ultimately in the quantum physics of the horizon, and there light is a very good system to do that. Because light, first of all, it's a clean, simple quantum system. Second, for technical reasons, so it's easy to detect light. So you have high efficient photodetectors. Even human eyes are able to see single photons. And so if we would see some radiation coming from, yes, we can detect it. The disadvantage of light is that light is pretty fast. So even in materials, so you could imagine that we are placing this fish now really with light propagating in the materials. It's possible to, well, in a material reduces the speed of light, so it's possible in principle to reach it, but it typically reduces the speed of light not by very much, by the refractive index. So standard material, order of magnitude 1.5, and so that's all you can get. So this sounds like a very hard problem, but it is not. And here's the trick to do that. And this is a trick I invented. So what you do is, you imagine you have a fiber, like a telecommunication fiber, and you send in light beams in these light pulses through the fiber. So this is one of those pulses. And what this pulse does, it slightly changes the refractive index of the fiber. So it adds a little bit to the refractive index. This is known as the Kerr effect. It's a nonlinear optical phenomenon. And so the light pulse adds a little bit of refractive index, and it moves through this fiber, as if you had an additional piece of material that would also move through this fiber. But there's no material moving, it's only light that is moving, and because it's light that is moving, it quite naturally moves at the speed of light. So it is actually very simple to create a situation where you have the impression that a piece of material is moving at the speed of light, because you can use light pulses in nonlinear optics to do that. Now, what can you do with this? So you could imagine the following scenario. So here's one light pulse that is moving through the fiber. Let's probe it. Let's send some wave after this light pulse, and suppose that this wave is a little bit faster than the pulse. So it tries to overtake it, but then it is slowed down because the refractive index, where the pulse is a bit larger. So it's slowed down by it, and until it reaches a point where it cannot overtake the pulse anymore, this is the horizon. And then what it does, it will change its frequency, because the wave coming in, it gets a little bit squashed, and that means its wavelength becomes shorter, its frequency is shifted towards the blue, and then it reaches the horizon, it falls back, and while falling back, it continues to be frequency shifted. And so that's something that yet you can detect in the laboratory. That's a shift of frequency at the horizon. That is a remnant of the blue or red shift that a horizon can do. This is one set of experiments that you can do with it. And the second, this is not a quantum experiment. The second experiment is then rather not to do anything. So not to send a wave after your pulse, but simply to wait for the quantum vacuum to do the job. So it will also move past the light pulse, and then it will create particles. So it will create photons, pairs of photons, and those pairs of photons, this is the signature that we want to record in the laboratory. So these types of experiments you can do with artificial event horizons. But before I come to the experiments, I want to add one more interesting physical picture, because it's related to the previous talk I gave in the morning. And so it turns out that when you talk about propagation of waves in one dimension, in particular propagation of light in a one-dimensional moving medium, you can describe this as a coordinate transformation as well. But it's a coordinate transformation of space and time. And so you see this, so the characteristic quantity that describes a wave, the characteristic time of a long pulse, consists of two components. This is laboratory time, and then the inverse integral of the velocity that your light experiences. Now the velocity is given in terms of the relativistic addition theorem of velocities, and so this defines a transformation of coordinates. So you go from laboratory coordinates like t and z, and then you get new coordinates t prime and z prime, and there you have a transformation of coordinates that is made by a moving fluid. And what I would like to do is I want to visualize this. So how does it look like? And
Z prime is just moving the reference frame?
No. So this is more complicated.
Transformed by
it would be. So if you would have uniform, so if your velocity of the medium would not change, or the speed of light would change, it would be the co-moving frame. But you don't. But you are actually in a situation where it is changed. So it's not a co-moving system.
What are limits in integral?
Sorry?
What are limits in integral?
They are constants. So so this defines your phase. So they are not important. It's some constant. Any more questions? Yes, please.
Why is there no Lorentz factor?
Why there is a Lorentz factor. So there's the addition theorem of velocity. And so you're asking why there's no Lorentz factor in front of it.
Yeah.
Well, the Lorentz factor, so this is, I cannot answer this, so...
No. Basically, it drops. That's the correct statistics standard deviation formula.
Is that some proper time?
So you have dx over prime over dt prime, and then relativistic factor simply drops. Dx prime has the same Lorentz factor.
In any case, so this is what you find. So you do the honest calculation, and that's the result you get. So the characteristic times are given simply by the relative velocity, but they are relativity enders. So you need to apply the proper relativistic addition theorem of velocities to get there.
And also,
yes?
Is c supposed to be multiplied by n or divided by n? It is multiplied by n in denominator.
Okay, so this is because of the relativistic addition theorem. There you have the two velocities, the product of the two velocities divided by c squared. So this is, so the non-relativistic addition theorem of velocities is that u plus minus c over n. And then you have the relativistic correction, that is u times c over n divided by c squared. So therefore you get it in the denominator, right?
And what is n?
The refractive index. So
C over n divided by c squared. Easy.
Yes, yeah, absolutely. So thanks for asking this question. So to slow me down. So n is the refractive index. The speed of light in the materials given by C over n, and hence, if you apply the relativistic addition theory of velocity, where this is u times C over n divided by c squared, that's what you get.
So what's the physical meaning of constant given by integral?
The constant of that integral.
Yes. What
It gives you an origin. You can always absorb this constant into time. So it gives you simply an origin of time, how you count time. So I want to have time should start now, or time should have started an hour ago. That's what this constant is. Really, it's not important. What is important is simply how space and time coordinates are related to each other, not what their origin is. Right, so I want to visualize this. So I want to show you, so how do you plot a space-time transformation? So the problem there is that space-time diagram is infinitely extended. But there's a nice trick due to Penrose of how to make it finite. And it goes like this. So you start with the Minkowski space-time. So this is space. This is time. And then you introduce the coordinates under 45 degrees in the space-time diagram, and you contract them. So these are the coordinates, t plus minus, t minus plus, c over c. And then you apply some transformation to those coordinates that take an infinite long interval and make it finite. So for example, the Arcus time length would do it. So what it would do is would generate a rhombus instead of the infinitely extended plane of space and time. And this is a picture of the entire space-time for you. The advantage of these pictures is that you can then, in a pictorial way, you can show what is the horizon there, what is the singularity, so it allows you to have a glance at the whole of space-time in one picture. That's its main advantage. Now, let me show you how the horizon of this scenario would look like. So let's assume we have a velocity profile like this. So we start from here low, some velocity, and then around the horizon it's getting faster in negative direction, so the velocity would drop. This is the horizon, and then would drop even further. So let's assume a profile like this, and generate these diagrams. This is the picture you get. So these, pay attention to these red points. So there are points in space, and so this is the point in front of the horizon after the forming the Penrose diagram with the proper transformation of space and time by the moving medium. And you see that it very much remains space-like. So it's a little bit deformed in its trajectory around space and time. However, on the other side of the horizon, it lies completely flat. So this is a visualization of what is often said, that beyond the horizon of a black hole, space and time, they exchange each other. So what is a point in space now really lies completely, lies almost flat, and so therefore it appears as if this would be time-like and not space-like. And so these Penrose diagrams, they have the property that they preserve the causal structure of space-time. So light rays are always propagating under 45 degrees in the space-time diagram. That is the feature that is preserved, so it's like a conformal transformation of space and time. And so therefore you can very easily see what happens to a light ray. So if you have a light ray on this side of the horizon, then it would propagate along 45 degrees, so it moves from minus infinity to plus infinity, and it stays on this side of the horizon. If you would have a light ray that propagates against the current, then it would go like this. So it would cross the horizon, and then somewhere at the singularity it would get crushed at the singularity. On the other hand, if you have a light ray over here, you also see it stays on the horizon. So the Penrose diagram neatly separates what you see on which side of the horizon. What you could imagine is, you could also take this diagram and simply put it on top of each other. So you could represent it like this. So that would suggest that to a light ray on this side of the horizon, you also have a partner ray on the other side of the horizon. And that's an important feature in the propagation and the scattering of light waves. And because it depends on what you look at. So it depends on what is your input and what is your output state. So if you observe light, then you are necessarily confined to either side of the horizon. So you see either light that is on this side or light that is on the other side. On the other hand, the quantum mechanical vacuum explores both sides of the horizon. So it belongs to a visualization where you put the two branches of space-time on top of each other. That's one thing you see. Another thing is that there are different frequencies involved here. So frequency is counted, if I may go back. So this is like a time parameter, so you go there from minus infinity to plus infinity. So frequency is counted in this direction. Now, if you look at this picture, so frequency would go in this direction, but on the top sheet, it goes actually in the other way around. So if you move from here to there, then on the top sheet, you would move from, not from minus infinity to plus infinity, but from plus infinity to minus infinity. This means that a wave that has positive frequency on this side of the horizon has a negative frequency on the other side of the horizon. So what you get is, in the quantum mechanical vacuum input states of the system, they are confined to, or they experience the space-time structure like this, and the waves that you observe experience the open space-time structure as shown on the other side. So they experience a mixing of waves with positive and negative frequencies, scattering of waves of positive and negative frequencies. And this gives rise to amplification. So you have access to negative frequency, that means negative particle numbers, and hence you are able to make particles. Okay, so this is simply an aspect I want to show, to see that there is a connection between ideas that come from spatial transformations and ideas related to horizons. The important new features of the horizon is that it's a space-time transformation and not just a spatial transformation. Let's go back to what you can actually hope to achieve in the laboratory, or what has been achieved in the laboratory. So about experiments of this kind where you want to probe the physics of the event horizon. So in order to, it sounds like a very simple idea that all you have to do is you put in light pulses in fiber and see what they do. In reality, if you want to have a chance to see very big effects like the analog of Hawking radiation, you need to have sophisticated systems. You need to have the best ultra-fast laser money can buy, and you need to have sophisticated fibers, or sophisticated waveguides. So these waveguides are so-called photonic crystal fibers. They have been invented by Philip Russell, and these are ultra-fast laser systems. The laser system we work with has pulses in the order of 6 femtoseconds, and that's something you need because you want to make photons and by very big effect. So these are essentially the Ferrari of lasers, and they also carry the price tag of a Ferrari. However, when I started to work in this field and took my first experimental steps, we didn't have the money to buy a Ferrari. We bought something like this, and but yet it worked. So this is the experiment that we did. This was with borrowed equipment in a borrowed laboratory. So you see the yellow tape. This was to fence up this part of the experiment from the postdoc next to it, to prevent him borrowing some of the materials that we were using.
Like crime scene that you...
This is the crime scene, precisely. Now, the blue spool that you see, this is the fiber. So we had about 2 meters of fiber wound around in a spool, and then there were light pulses coming from this laser. So this is in a laser facility. We didn't need to pay for the laser. These were 100 femtosecond pulses, and they were then sent into the fiber, and I don't remember by which part of the optics. And then we had our laser that is the equivalent of this here, and this is the. I would not recommend anyone to buy this laser. So it's very difficult to operate, but it is cheap. So this is the laser we use to feed radiation in, and then we tested the spectrum with the spectrum analyzer. This is what we got. So this is the spectrum with and without the pulses. We subtracted them, and then you got these features here. So you see two phenomena, so two variations of the spectrum. This is the blue shift that is created by experiencing the event horizon at the end of the pulse. But then also there should be a gap in front of the pulse, because the whole fiber is filled with light. This light is a little bit faster than the pulses, and so it can escape from the pulse, so it forms a gap in front, and then a blue shifted part in the trailing end, and these two parts of the spectrum there correspond nicely to it. Now, let me explain the theoretical pictures behind this and other experiments in connection with it. And it's in fact not difficult. So most of the physics is fairly simple. It can be traced back to a discussion of the Doppler effect. So we distinguish two frequencies. One is the frequency in the laboratory frame. The other one is the frequency in the co-moving frame. And here we don't have a relativistic factor in front because of the, we could have, but because of the transformation we're doing, we're not performing a Lorentz transformation, we are just performing a Galilei transformation. It doesn't matter in the analysis of the physics. So this is a Galilean Doppler shift, and so we need to discuss these two frequencies. If you take the dispersion curve of the fibers, so how the refractive index varies as a function of frequency, and plot it as omega prime as the Doppler shifted frequency in the laboratory, in the co-moving frame, then you get a curve like this. So these are typical curves for our setup, and they have some characteristic features I'm going to explain. So the first thing you can see is you take Doppler's formula and you differentiate. You can do it in your head. So you differentiate this formula, and you see that on the left-hand side you get d omega prime, d omega, and then on the right-hand side what you get is minus the velocity divided by the group velocity. So this means that if the left-hand side is 0, then the points in this curve that correspond to that, they have the same velocity, so their group velocity is the same as the speed of the pulses. So they have the same velocity as the pulse. So the extrema of this curve, they share the same velocity, in particular the pulse itself. If you would differentiate it twice, then you can convince yourself that it depends on whether you have normal or normalist group velocity dispersion. In order to keep the pulse stable, you need to have a normalist group velocity dispersion. So that means that the pulse always sits in the minimum of this curve, and then you have around it two other local maxima, and they are horizons. So you have two sets of horizon, one for higher frequencies than the pulse and one for lower frequencies. The one horizon we work with is the one on the lower frequency side. That's a horizon. So then the advantage of these diagrams is that if we talk about the propagation of pulses in the fiber, you have a conserved quantity. Conserved quantity is not the frequency in the laboratory frame, because in the laboratory frame things change in time. But it's the frequency in the co-moving frame, because in the co-moving frame the pulse would simply sit there and would do nothing. So omega prime is conserved. That means you can discuss, so everything that does happen, happens at a line of omega prime equal to constant. So we can discuss of what kind of frequencies you can achieve by this. Now, imagine the light wave comes in and is then frequency shifted. Then what you can say is that the refractive index here gets an additional contribution. This additional contribution comes from the light, so it's proportional to the intensity to it. And you can rearrange it like this, that it corresponds to the meeting point of two curves. One is the curve I showed before, so that comes from omega prime and is given by dispersion of the fiber. And then you have another linear curve to it that corresponds to the contribution that comes from the intensity of the pulse. So in order to predict what happens, you start with this curve here, so with the horizontal line, and then it moves up to the horizon and it moves down. And that gives you these 2 points. So this is the initial point and then you get the blue shifted frequency over there. So that gives you a prediction of what kind of frequency shifting do you get. So in this way you can explain the experiment I showed you about frequency shifting at the horizon by these 2 points and the way to get there. Now you also see another feature from the diagram. So not only do you have a wave on, that is running towards the horizon, not only do you have then another wave that is potentially blue shifted and that you can blue shift by letting it run against the horizon, you also have a wave with negative frequencies. So that is also allowed. So in principle, you can scatter your incoming wave into a wave with a negative frequency as well. And this is what gives rise to Hawking radiation. So it corresponds, positive and negative frequencies correspond to the following 2 cases. So if you have positive frequency in the laboratory frame, you get a positive frequency in the co-moving frame if the phase velocity is lower, if the velocity is lower than the phase velocity. So then, the positive sign remains a positive sign. On the other hand, if your light is slower than the speed of the pulse, then you get a sign change. So positive frequency in the laboratory frame correspond to a negative frequency in the co-moving frame and vice versa. This matters because what kind of frequency you have determines of whether you have in the expansion of the quantum field, whether you have annihilation or creation operators. So it distinguishes between what part of your quantum field of radiation correspond to annihilation and creation operators, and because it's the ones with the positive frequencies that give you rise to the annihilation operator, the ones with the negative frequency that give you rise there, or the complex conjugate ones, which is negative frequency, give you rise to the creation operator. So if you have a process that mixes positive and negative frequencies, then what you get is the mixing of annihilation and creation operator, and this corresponds to the creation of particles. Another feature that arises is that the Kerr effect, so the nonlinear effect, is also acting on the pulse itself. So it has a tendency to slow down the peak of the pulse, and that means you get sharp fronts at the trailing edge of the pulse, and in extreme cases are shocks, so potential for optical shocks, and that gives you very sharp changes in the refractive index, and these sharp changes can lead to more rapid coupling between these waves and therefore to a higher degree of Hawking radiation. So this is a hand-waving argument why you need very, very short pulses, and then if you have them, there's a tendency the system makes them even shorter. So that's another thing that could work to your advantage. So this is part of the theory. Now I want to discuss some of the experiments that people have done and that we also have participated with. This is an experiment published in 2010, and that was inspired by our theory and our experiment, and it represents another simplification of it. So here, not a fiber was used, but a solid piece of glass, and light pulses were sent into the solid piece of glass. It turns out that these pulses can also guide themselves, so they create their own wave guiding effect, and you can do this in non-linear fashion, but there are also optics of linear optics, how you can keep these pulses at place. And so they then propagate through the piece of glass. They don't need any waveguide anymore. You can control their velocity by the lateral field patterns you give those pulses. And then the experimentalists observed radiation coming out to the side, and this radiation it agreed with what they expected from Hawking radiation, so it was claimed that this is an observation of Hawking radiation in the laboratory. Where does this lie in terms of our diagram? So this experiment probes this point. So it is zero frequency in a co-moving frame. This means that the radiation that we are seeing is when you exactly reach the phase velocity of light in the material. Now, the problem with this experiment is that the effect is too large. So it disagrees with theory by several orders of magnitude, so they shouldn't have seen this radiation. So what did they actually see? What was seen in this experiment? So there was a comment related to the experiment, and in this comment I believe the question, I don't believe the answer. So this is something that we are working on at the moment. We're trying to get an answer of what was actually seen in these experiments. We're doing this both with experimental and theoretical means, and the story is not finished, so I cannot give you the answer. What I know is that it's a very interesting story. So we have discovered some very interesting aspects of the physics involved, and let's see what comes out of it. So this is one of the discussions going on. I would like to show you another experiment that is not an optical, but an experiment done with fluids, and it's a measurement of stimulated Hawking radiation in an analog system made of fluid, and it looks Victorian, so it's like a drawing from a textbook from the 19th century, and it's done with a water channel. So you see, this is the setup. So it's water flowing, here's a pump, and it spits out water into this system. Then this water runs over a flume like this, and then it gets down and gets pumped, and so on and so forth. And they create waves. This is a wave maker where simply a sheet is dipped into the water, and it's then sending waves against the current. The flume is designed such that you exceed the speed of the waves at a convenient part over here of it, and such that you can make observations. How did they make observations? So they use water, they put some dye into it, and then illuminate with a laser sheet that you see a strip on the surface glowing, and then take a video of that. So this is a video and space-time diagram of that video, and then the interesting aspect, they Fourier transform it. So it's a Fourier transformation in space and time, and then if you Fourier transform it, you see the characteristic wavelength and frequencies involved. So first of all, you see the frequency made by the wave maker. So this wave maker is then sending the waves against the current, and so this is this frequency. And then from the curve, you can take various components. So you have, I think this is the original component, then you have a blue shift component, and then you also have a component that is that belongs to negative wave numbers, so negative frequencies, if you like. That's what they extracted for the Fourier transform. They fitted this to an exponential curve, and it seemed to fit the prediction of a thermal radiation from a black hole reasonably well. However, I should also say that there's doubt on that. So it's always very, this is a Fourier transform of a logarithmic plot. It's always very easy to get some exponential dependencies, and so it is also possible that this experiment was contaminated by other effects as well. So this is being re-investigated. There are other experiments to try to see to what extent you could even see some aspects of the physics of the event horizon, even closely related to quantum physics, with a simple water wave experiment. Now let's go back to optics. So this is another experiment. This is an experiment I was involved in. So where we showed one crucial component to the generation of photons at the event horizon. That is this component of negative frequencies. So normally you have, when you send in ultra-short light pulses in a fiber, what you see is you see a generation of waves of higher frequency, lower wave numbers, so some bluish light coming out of it, and that is in the literature called Cherenkov radiation. In reality, it has nothing to do with Cherenkov radiation, but unfortunately that term was created. So it's some dispersive wave that is created by that the pulse is able to also tunnel into a new kind of wave that, because it has the same energy, and that is then blue towards it. And this is what you can observe. This is a piece of fiber, and you see you send in the light pulse on this end. It looks reddish, and then it becomes blue on the other end. So that's known as dispersive wave or Cherenkov radiation from light pulses. Now, what these two girls have observed was in two different related experiments, generation of waves that belong to negative frequencies. And so this peak sits in its spectrum there where you would expect the negative frequency component to appear, and so that would correspond to the, an observation of that some light of the pulse is also transformed into a negative frequency wave. This is an important component of Hawking radiation. So this was the state of affairs before I moved to the Weizmann Institute. And so what we are doing right now, we have rebuilt, not only rebuilt, we built up the experiment to be able to do this much better. We are now in a position where we have reproduced all the effects I've shown you, and we are going into an observation of new things, and we do this thanks to very sophisticated equipment. For example, in order to observe the photons generated by the event horizon, we use these kind of detectors. These are superconducting nanowire detectors, where the superconductivity in a nanowire is switched off due to the heat of a single photon. This is something absolutely incredible experimentally that this is possible, and it allows you to detect infrared photons with a very low degree of noise. So this is something that we definitely need in our experiments. We also use this kind of setup for ultraviolet detectors. There again, there's zero noise, so these are very, very good detectors, and hopefully with them we have the right tools to observe Hawking radiation. We also spend a lot of work on the theory of this, so we understand now where in the spectrum we do expect radiation and how it should look like. And what we found is that essentially the Hawking radiation occurs at the interesting points related to dispersion. So whenever you have a horizon, and I told you there are several horizons, the pulse itself is a horizon, then there is one horizon over here, it's at low wavelength, and then one horizon at shorter wavelength, and you see peaks in the spectrum due to Hawking radiation where you have a horizon. Here, of course, everything is swamped by the radiation of the pulse, so the only horizon you can realistically hope to explore is this one. And then it has its partner, and its partner is in a UV, and so we know where we would where you would expect Hawking radiation to observe. And what we are in the process of doing is to build up an apparatus such that we can correlate photons. So whenever we see a photon here, we can also see whether there is any photon on the other side. Hawking radiation should always be correlated. So the photon on one side of the horizon is created simultaneously with a photon on the other side of the horizon. And these correlations, they will allow you to get rid of the noise, so that you have you get some order into the many, many photons that realistically are generated, are existed in these systems. So this is work in progress, and hopefully we will be able to see something meaningful in the near future. And before I close my talk, I want to quote from preface to the book of Richard Wollerwick on the universe and the helium droplet. The preface was written by Björken, and it characterizes this field. So it says, so far this is not respectable territory. So there is danger to the young researcher venturing within. Working on it may be detrimental to its successful career track. But together with the danger, there will be high adventure, and if the ideas turn out to be correct, great rewards. I salute those who take the chance and embark upon the adventure. So I would like to salute the people who are working on this. Thank you.